Good day, everyone. My name is Lasitha Chamari. I'm from Information Systems in the Built Environment Group, Eindhoven University of Technology, Netherlands. So today, I'm here to present our paper on Extensible real-time data acquisition and management system for IoT-enabled buildings, together with my two supervisors, Professor Ekaterina Petrova and Professor Pieter Pauwels. This is the outline of my presentation, so we have 7 sections. Let's get started. So when we say smart buildings, we are talking about a lot of sensors, networks, cloud, analytics, users involved in the smart building. And what's basically going on is we have sensors in the building, so we acquire real-time data from the built environment and then send them through the network to the cloud, do some analytics, and that data is the input to a lot of algorithms to fine-tune the operation of the building, and then those controls are fed back into the building to keep the built environment in optimum conditions. And IoT plays a special role in this because they help us to capture the data in real time, do the analytics, and also communicate from within the devices in the building. In fact, building management systems are also becoming cloud-based, so potentially becoming IoT devices themselves in the building. So what we usually see when we hear IoT is some image like this, where everything is interconnected to a single IoT platform, where everybody can talk to each other and collect the data and send them to the cloud at a single point, which makes life easier for the building engineers. But what we see in reality is this kind of heterogeneous IoT platforms, and mostly there's no master systems integrator if it's not there. What we usually see is some heterogeneous platforms like this. So in this case, we have 3 platforms. Let's look at some examples on how to access these different platforms and what kind of messages that we get. For example, if I want to connect to the data stream of this particular IoT platform, I need to access this endpoint, and this is the message that I get. So this is from an air quality sensor. So we have a lot of key value pairs, nested items, and then values. And this is another example. This is for a smart socket, and this is the access point for this access URL for this smart socket, and this is the message that I get from the IoT platform. Also, we can already see there are heterogeneous IoT platforms and different methods that we need to use to access these platforms. And if we closely look at the structure of the messages, in the first one we see an H, and its value is 46.8. So is this humidity, height, or something else? I don't know for sure. And if you look at the second one, it says add_ELE, a value of 19. Is it electricity or something else, which is very ambiguous. And if you look at again, there's a T in the first one, which is 21.9, could be a temperature, and in the second one, it's T, which is a huge value, which is a timestamp. So why do we use T for describing temperature and timestamp? So it's very confusing. And there's a value of current voltage, which is 2029. So I'm wondering why it's not 230 volts and 2029. Is there a over voltage? Is it a fault, or is it an error in the conversion in the IoT platform? So a lot of these kind of problems arise when we try to tackle the IoT streams in buildings. So the first one is different methods to access, a lot of heterogeneity, and within the messages itself we see a lot of ambiguities because the semantics are not standardized. IoT is not for metadata, it's for communication between machines. So optimum messages, low number of characters is like the default choice. So what we identified as problems is a lot of heterogeneity in IoT platforms and lack of standardization. It's not like it's not a field bus like Modbus or Backlit. So there's no standardization into what you can put inside the message. So different platforms use different methods and different structures inside the message. And the second question is, there's no sufficient metadata for integrating with each other information systems, and also there's a lot of ambiguity because of the semantics. For example, if I want to see where is that socket located, where there's a high voltage reading, I have no clue which room or which equipment it is connected to, because it's not linked to those information systems we already have. So this leads us to ask these questions: how can we integrate these heterogeneous platforms that we have in a smart building? Second question is, how can we improve the semantics and interoperability so we can link them with other information systems that we already have in buildings? And the third question is the most important question: are we going to do that, answer those research questions 1 and 2 only for these 3 platforms and this building only, or are we going to develop it so we can reuse it for other devices, other platforms, and other buildings? So are we going to make it extensible? That means we don't have to destroy what we already have, the code, to make it available for another building, or for if we have another IoT platform coming in. And these research questions leads to the methods. First one is how to integrate them. So we develop a framework for integrating these different IoT platforms. Second one is we are adding semantics to these IoT streams to improve the understandability and also integration with other systems. And third one is, like I said, we should be able to make the solution an extensible one or a scalable one. So we are looking at a solution architecture, not just one and done project for this particular use case. And then we have a resulting data acquisition and management system, and we have a proof of concept implementation. So let's look at the first part, the integration part. So we start with data providers. That means these kind of heterogeneous IoT platforms in buildings. And in the second layer, the data acquisition layer, we try to get the original data as it is that is coming from the IoT platform and publish them to a message broker, for example, like MQTT broker, without changing anything. So we just keep the structure as it is, but we publish all of them into a message broker. That means we need a different connector for each type of IoT platform to begin with. And then at the message processor level, this is very important. So this is an example of a message that we get. So in here we have a timestamp and we have key value pairs. Some of them are plain, some of them are nested. What we need to do is, when we want to transform it to a uniform structure, we try to flat map the payload or the message content. And if it's a MQTT broker, for example, we have an MQTT topic, which is the identifier of that real-time stream. So we add that MQTT topic to the payload, and also we add timestamp, regardless of it already have a timestamp or it doesn't have a timestamp, because not always there's a timestamp involved in the message itself. And the new message structure looks like this. We have the topic, which is the identifier of the real-time stream, and then we have an array of keys, and then we have an array of values that are associated, the values of those keys. And then we add the timestamp, that is the timestamp that the message is received at the message broker. And the resulting message looks like this. So we have a JSON object which includes the topic, keys, values, and a timestamp. So from this point onwards, every message looks like this. So then again, those processed messages are published into a message broker, and if you access this message broker, then we have a uniform structure to all the messages that we get from the IoT platforms. So at this level, you can directly access the message broker, or you can record them in a historical time series database for later usage. And I want to emphasize at this stage, each of these services that I described earlier, they do one thing, and that one thing very good. That's what we want to do when we go to an architecture like microservices. So they are assigned a job, and that's the only job that they are going to care about. For example, if at data acquisition stage, they just take all the messages, publish them to a broker, and the message processor listen to all the messages in the MQTT broker and translate them. That's all. And the research question 2, how can we add the semantics to understand them better and also integrate with other information systems? So at this level, we are looking at ontologies in smart building domain. For example, bot ontology, SSN ontology, and brick ontology. This is part of one of the sensors, IoT sensors. And first we need to understand what do we actually need to model using these ontologies. Because some things are special to IoT. For example, if we take one IoT node, like an air quality sensor, this one measures 8 parameters. So it's a one node measuring 8 parameters, so it has 8 sensors. We need a way to model that. And there are several candidates, SSN hosts or brick hash point or SOSA made by sensor. We can use them. So in this case, I'm going with brick hash point. So there's a particular sensor or an equipment and it has 8 points. And the second one is we need to identify each IO stream uniquely. That's why we included the MQTT topic in the payload in the previous stage. So at this stage, we can use bricks hash time series ID relationship, and this is the MQTT topic that I have included under that particular IoT node. And other things are more general. Like I said, I need to know where this sensor is located, so what is the location of this sensor. And we can use, again, multiple ontologies, brick hash location, or SSN deployed on platform. In this case, I'm going with the location. So this is the part of the graph that is very relevant to this particular IoT node. So assuming we already have a semantic graph of the building already built using bot ontology or IFC to RDF converter, or we have mapped the building management system using brick ontology. So we can integrate this component with an existing graph, or this can be a graph on itself. So we have, in this case, IoT domain in the left side, so we integrate it to an existing graph. We already have that describes the topology of the building and the MEP domain and BMS domain. Third question is the extensibility. So far we identified several components. We have data providers, we have a message processor, we have a real-time stream, and we have the semantic graph in a graph database. We have historical time series data in a time series database. So how do we talk to each other? How do we make the connection between all these systems? This is where we thought a solution architecture would be better, so we can scale it between buildings, or when we have multiple IoT platforms coming in, we only need to implement just one another connector. So that translates the original messages to our message broker, and then that's it. And here we are talking about also an API, because we are talking to different databases. So if we combine all them, we have this framework or a system architecture. In the top, we start with different IoT platforms. And in layer 1, we have different data providers, which translates the message to an MQTT broker, and which is the layer 2. In layer 3, we have the message processor, which translates the message to the uniform format that we need, plus the other message broker that these processed messages are published to. And in the bottom, we have the smart building applications. It could be a dashboard, it could be a digital twin, it could be a real-time prediction algorithm, which need to access those real-time data at the top. And what it does is we have all the descriptions or the relationships in the semantic graph. So through the API, the application requests the graph database, can you give me the identifier of this particular IoT stream of this smart socket that is located in room 123. And it gives you the identifier of that real-time stream, and it can use that particular ID or the MQTT topic in this case to listen to the real-time data stream. This is the proof of concept implementation. So we use Atlas building Eindhoven. We introduced these 3 IoT nodes, the air quality sensor, smart plug, and one of our own IoT devices. And we have the semantic graph of the Atlas building. So we have an API with several endpoints to talk to the graph database and time series database. So in the end, we have an application like this. So first it queries for all the buildings in the graph, and then we have one building, Atlas, and then it queries, given the building, what are the floors, and if we click on a floor, we get all the rooms of that particular floor. And this is the Sparkle query that runs in the behind, so you get all the rooms and the sensors associated with them. And then you ask, when you click on some kind of a sensor of your choice, then you get the real-time stream ID. And then you use that real-time stream ID to connect to the real-time data server. In this case, we implemented the Socket.io server, and then you get the real-time data of that particular sensor. So to conclude, we started with 3 questions about how to integrate different IoT devices and platforms. So we used a message broker and a message processor to unify them. And the second question is how to improve the semantics and interoperabilities. We use smart building ontologies to make a semantic graph and link it with other information systems. And to make it an extensible system, we used a solution architecture based on a different kind of database, graph database, time series database, and a REST API. So in the end, it's extensible, a real-time data acquisition and management system for IoT-enabled smart buildings. Acknowledgement goes to Brains for Buildings project. This is the project for funding my PhD, and also for the nice collaboration that we have, and also ISB group of TU Eindhoven for all the nice meetings and collaborations. This is part of reference. You can read them in the full paper. Thank you so much.